have Jonas Neubert, who's going to tell us what a PLC is and explain why there is a giant pile of wires on the stage. Please make him welcome.
Thank you. I've given a handful of talks at other Python events, and if any of you were there, you will know that I have this weird habit of talking about Python in the context of factory automation. And I'm going to do it again today, so I figured I might as well start with a quick story about why I keep harping on about this weird topic. So for me, this actually started in high school, and I somehow finagled my way into this internship at our local semiconductor factory. Now, if you've ever been to one of those places, they are freaking amazing. It's like these massive halls full of high-tech equipment. And since then, I have been fascinated by the role that software plays in building these very complex machines, which we call factories, and that make virtually everything around us. But I also noticed that I seem to have stumbled upon this weird niche. Like most software developers never even hear about factory automation as a topic that they can apply their skills to, and if you come to conferences like this one, the topic has a really low profile, and the same is true for like blogs and podcasts and all these other places where software engineers exchange information. So I figured maybe I can do a little bit to change that. And 3 years ago, I started to, every calendar year, prepare a conference talk about a factory automation topic for an audience of software developers. And this year, the topic that I brought is PLCs, which stands for Programmable Logic Controllers. Now, if you've ever asked anyone who's actually worked with one of those things, these PLCs, what their first association is, they will tell you factories. Because if you walk around a factory like this one, you keep an eye out for these metal boxes, the electronics panels, and they have a couple of readouts and buttons and dials and stuff on the outside, and if you open them up, it's quite likely that you'll find a PLC on the inside, controlling a robot, or like in this case, a standalone window tinting machine. Of course, you guys don't have access to car factories, most of us don't, so you can also find them everywhere else. Wind turbines, construction cranes, amusement parks, car washes, escalators. In every city, there's PLCs controlling the HVAC and the elevator of most buildings. At this point, I probably have you believe that there's a PLC in every box that you find in the street. That's actually not the case. This is an example of a control box for a traffic intersection with a signal. And those are really quite simple in terms of the logic that's going on, and there's thousands of them all over the country and the world. You can actually buy fixed electronics off the shelf, and you don't need any programmable logic. There's nothing custom in it. Except, of course, when your intersection is part of a traffic management system that's capturing the whole city, or you have a tram crossing, then your logic becomes custom again. You need programmable, so you might be using a programmable logic controller. You might have heard that thing where if you're in a big city or in a small town like Petaluma, you're never more than 10 feet away from a rat. I'm gonna add to that. I'm gonna add to that urban myth, and I'm gonna say you're also never more than 50 feet away from a PLC. And with that as motivation, here's the outline of my talk. Super simple. It's actually in the talk title. First, we talk about what's a PLC, and then we talk about how can I talk Python to it. Some of my slides are super busy because I want you to use them as reference after the talk is over. So use this link here to find them, or I also just put a link to them on Twitter if that's easier to type. I'm going to start by just going through what happens when you're an engineer in automation who wants to work with a PLC. So step 1, you figure out which PLC you want. Step 2, you ask for a quote. Step 3, you go to your purchasing department. Anyway, lots of paperwork. The box arrives, you open it up, and you find one of those things. Depending on your budget, it's one of those cheap fixed feature set ones, the compact ones. Or if you do something really fancy and you have a big bag of money, you might buy one of those expansible ones where you buy the main unit and then you keep adding these modules until you have all the functionality that your requirements demand. You'll be spending a week or a month or a year installing the thing. It looks like it's grown a ponytail, or 2 or 3. Those are wires that someone connected to them. And these are stock photos. This is what it looks like when a professional does it. I actually brought a PLC today, and it looks distinctly different when I wire up my PLC. So this is the one that we'll be using for the demo in a little bit. I do realize I haven't told you what a PLC actually does. The wires are the first hint. So we talked about how PLCs are programmable, so they definitely live in the world of software with bits and bytes. But the wires connect them to field devices, and those aren't like Ethernet wires or anything. These are just electrical wires. So the other side of the world that the PLCs have the other foot in is the physical world of atoms and electrons. And the PLC is one of the devices that lives right at that interface. I mentioned field devices. What's that? It's a fancy word for sensors and actuators. And you all know a sensor is the kind of device that takes a physically observable phenomenon from the real world, turns it into an electrical signal, and maybe we can turn it into a variable later on. And an actuator is sort of the reverse. We might start with a variable, we turn it into an electrical signal, and the actuator has an effect on the physical world. I made this slide, took me forever. The only take home here is there are lots of different electrical signals out there. In fact, that's where this whole modular business I talked about earlier comes from. You can't just wire any wire up to any port on the PLC. You need to buy the right hardware that supports the type of signal you're working with. We're not going to do an intro to signals here. That was actually a semester-long class in my undergrad. What I want you to remember is that there are digital signals that are either on or off, and they might turn into a Boolean variable later on, and analog signals that need to be sampled more precisely, and they might become a number in our code later on. And then we have inputs from the sensors and outputs to the actuators, which leads to cool abbreviations like DI for digital input, AI for analog input, DQ for digital output. Yes, there's a Q there, and that's just a weird standard in automation. I assume they use a letter Q because the letter O looks too much like the number 0. So we've purchased it, we wired it up. What does it do? Like every computing device, PLCs go through the IPO cycle. We actually heard about that yesterday. Step 1, input, in the case of a PLC, is where it samples the electrical signals that come out from the field devices. It turns it into a variable. It stores it in a place in memory called process image in. Step 2, program or process. We execute some application program. Now, most programs that we write take input variables and compute output variables from them. The outputs get stored to somewhere else in memory. And then step 3, output for the PLC. That means take those output variables and write them back to the electrical wires as electrical signals to the field to the actuators to do something. This gets executed over and over and over again at a sort of fixed cycle rate. And the interesting part really is step 2, because that's where we can have an effect on what the PLC is doing. And also that's where the name comes from, because that's where this programmable logic lives. All right. Just to recap, we've established PLCs are the device at the interface of the world of software and the world of hardware, the physical world. They're wired up to field devices with electrical signals, and we can program them. So why don't I fire up my favorite text editor and start programming the PLC? Just kidding. PLCs are not programmed with text, and you also don't use your favorite software. You use the you use the one software that the vendor of the PLC gave you to program their brand of PLC. So I actually selected the PLC I brought today specifically because the programming software is visually uncluttered enough that I dare to show it on a presentation screen. You should check out what the other programs are. I'm also going to use this zooming in feature every now and then. So this is really the programming, like the editor window here. You see my cursor dancing around? On the left side, there's this vertical line. Imagine that's electrified. There's a voltage applied to it. And the electrons are trying to travel across these horizontal lines here. Now, we have the power to change their behavior by putting circuit elements like this normally open contact, which I tie to a variable called di1. Now you know why I was talking about signal types earlier. Now, if di1 becomes true, current can travel here where my cursor is. If di1 is false, it cannot get there. So we use that to put an output coil that we wire up to a variable called dq1. And basically, we've just built an if statement in this language. If di1 is true, dq1 will also be true. Now I go connect to my PLC, which I should have totally done before the presentation. Oh, moment of truth. There we go. And the goal is to send that program over to the PLC. What? That's good news. It's fine. That's all good. We sent the program over. I've got an Ethernet cable here, which connects my laptop to the PLC. So the program, hopefully, is traveling over there right now. Is that thing blinking? Nope. Yeah, that's not how the demo is supposed to go. I am going to power cycle this really quick. So we sent let's assume we sent that program over here and everything is good, right? We need to test it somehow. So how are we going to test this? Well, we need field devices. Normally at home, I would use like a little LED or something like that that's on my bench. I'm kind of gambling here because now comes sort of the big reveal, and oh yeah, it's working. So because you wouldn't be able to see the LED, I picked something up on the way here that will make this a lot more visible. Wow, this is good. It's not working. And then you test it a million times. I also brought us an input, so I'm going to wire this up. And I mean, that works, but that only works because I put the program on there before I started. So I'm going to take what? All right, let's try that one more time. There we go. This is the one we want to connect to. And now I want to use my program. I'm going to resume the talk by pretending that I actually need to send a program over the Ethernet cable, which I already mentioned. And now we can go and test it. 1%? All right, this isn't going very well. So I'm wondering if I should go to my backup slides. Maybe this is the point in time. One more check of the networking here and plug this in. All right, well, I don't know what's happening on this stage here. I tested this a million times. Obviously, the Ethernet cable doesn't want to do it. All right, so we programmed this. I press the button, the light comes on. Pretty simple. We can actually go into this monitor mode, network gods permitting, and you can actually see the variables change on the screen, which is a kind of a cool feature. One of the big problems in electronics is debouncing. Your signals, like when you change an input really quick, you get a bit of an undesirable effect here. So one thing we're going to do is we replace our output with a timer, and we say count up to 2 seconds, which is 200 in this weird language. We tie up some variables to that timer, and then we add a second rule, another normally open contact, where we say timer 1, like if timer 1 is done, then we want to switch our output coil on again, and remember that variable is called DQ1. Now we program that over again. And then the behavior, of course, is that when I press the button, nothing really happens, but you can see the counter counting up. And when it reaches 200, the light comes on. I let go, it resets to 0. Press the button again, it starts counting from 0 again, goes to 2 seconds, the light comes on. All right, after our quick technical snafu, you guys are becoming experts at this PLC programming business. I'm going to show you like one more little trick here. I add another row on top here. I add another timer. I'm also going to have that count to 2 seconds. I'm going to call it timer 2 value, and then I say timer 2 done is the variable that tells me if it's done. I'm going to add a rule here where I use a normally closed contact and say if timer 1 is not done, that's the strike through, it's a normally closed contact as opposed to the normally open ones. So if timer 1 is not done, then timer 2 should start counting. If timer 2 is done, I want timer 1 to start counting, and then if timer 2 is done, I also want the light to come on. And because you guys are all wizards, you can use the time while it's sending the program over to figure out what this might end up doing. Oh yeah, we got the hello world of any electronics project, a blinking light. One thing just to be clear is the logic is being executed on this PLC. The network cable is purely for sending the program over and doing this monitoring business that's going on the screen. In fact, and now I'm tempting the demo gods. I can unplug this Ethernet cable. The light will continue blinking. And of course, I lost my network connection, so you no longer see updates on the screen. Then I plug it back in, and everything will magically go back to normal, I'm sure. All right, so what did we... Actually, I'm going to stop this because that's distracting. What did we just see? Well, this was the screen. The language I made you an expert in is called ladder logic because it looks like a ladder. There's this, there are the two rails on either side, which are the vertical lines. They're connected by the rungs of the ladder, which are the horizontal lines. The neutral rail is not really shown in the software, so I put a little gray line here. The hot rail, it's called hot because you imagine it's under voltage. You touch it, it saps you, it feels hot. Also, the conditionals we put on there, we call them contacts, and the output variables, we call them coils. Why? This is why. Before the time of PLCs, the way you would program your control system is you buy a big bag of relays, lots and lots of wire, and then depending on how you connect these relays with wires, like the physical layout of your wires is actually the control program. Now, if you've ever worked with a relay, the two terminals that you wire up your input voltage, they're called contacts. When you switch the voltage on, you energize a coil, which electromagnetically switches a switch, which is the output variable. So that's where the terminology for ladder logic comes from. I know some people are playing programming language bingo. Listen to this. Ladder logic obviously is a very old language. It's been around for 50 years and inspired by terminology that's much older. So the likes of Pascal, COBOL, Forth, Lisp, all of those, they can step to the side. Ladder logic is the true elder statesman of the programming language. There are different views on the fact that it's still in very active use in industry. There's what I call the Hacker News view, where you think everything old needs to be disrupted, and you write things like, oh, these people are stuck in the technological dark ages. They are programming in ladder logic. And then there's the other view, where you actually you take this anthropological interest and say, that thing's been around for 50 years. Why? It must have something going for it. And that something is that ladder logic still is truly the common denominator across programming for all brands of PLCs. And it is part of the curriculum for automation engineers and technicians. And that last part really matters. Because if you work at an automation integrator, which is the kind of company that builds machines for factories, you ship the machine to the factory, it now becomes owned by the maintenance department of that factory. The people working there are technicians and electricians, and their job is to keep that thing running, sometimes for decades. So ladder logic actually is a language that's designed only for debugging and troubleshooting, and not at all for the people writing it, which is so different from any other programming language that I'm familiar with. We blew right past halftime with our little technical trouble here, but we still haven't seen any Python. So let's change that. For that, I go back over here, and I quickly open up a different program that I prepared. And what we're going to do is that we actually turn our traffic signal into a real traffic signal now. And obviously, there's a part missing that I also brought. All right, is the green light? Is the light on? Green light or something? Oh, because we're not running. There we go. So what this program does, let's see if we can monitor this again. If I press the button, you can kind of scroll down here, and you see that there's a number of timers that fire sequentially. And at the bottom, there's a bunch of logic that just decides which lights are on or flashing or whatever, what have you. So if you go back here, pick any one of those timers, you will notice that the value that we used earlier to define the length of the timer, like 200 for 2 seconds, I now put a variable here, or in PLC parlance, it's a tag. Now, variable names are a bit of a luxury in PLC programming. Back in the olden days, they had to use register addresses and stuff. But this program, actually, this programming environment gives us a tag database, basically all the variables that are in use in our program. So you see the DIs and DQs at the top, bunch of timers. And then down here at the bottom, they look a little bit different. some of those variables have this mod start and mod end address. So what's going on here is that we're looking at a protocol called Modbus, because shortly after PLCs were invented in the 60s, people realized it would sure be nice if they could talk to each other. So they came up with protocols where one PLC gives another PLC access to its variables. So PLC 1 can actually access variables in PLC 2 and change them, and possibly vice versa. So that's what Modbus and a whole family of other protocols that cropped up over the years do, and they are designed for having multiple PLCs talk with each other. Now, we live in the modern times, so we can make our computers pretend to be PLCs by installing packages like PyModbus, opening our REPL. I'm now trying to speed up with a whole bunch of autocomplete to open a client, that establishes a connection to our PLC using the Modbus protocol. This is the IP address that my PLC lives at. And we can do things like reading those registers that we were looking at, and we see those numbers here. Those are actually the timings of the traffic light. 2 seconds before the yellow shows up, 3 seconds of yellow, 1 second before the pedestrians get a walk signal, and so on. So the first thing I do with that, I realize I have write access, and I'm going to fix the traffic light. That's a joke that comes later, don't laugh about it yet. So I want to change the traffic light so that pedestrians don't have to unnecessarily wait. I'm going to tell it to only wait 1/10 of a second after pressing the button for the yellow light to come on and stop the traffic. So there's a whole bunch of zeros kicking around here, by the way. I don't have time to go into those. You just have to believe me, they are necessary. We're sending that over. We're going out to the street to test. Press the button, almost instant yellow. This works. People in our town get word that we are the ones who know how to change traffic light timings. The treasurer comes to our office and says, you know, we installed that red light camera that never catches anyone. Can we make the yellow shorter? And we suspend good judgment just for a second and say, yeah, sure, we can do that. Let's make it 1 second instead of 3. And we set that over there. We go test 1 second of yellow, then it goes to red. Next day, safety officer is right in our office saying, we have to do something about those pedestrians getting hit by cars all the time. So you're like, all right, there is that phase where the red light is already on, but the pedestrians aren't allowed to walk yet. It's like a safety buffer. We make that longer. Let's make it 4 seconds. We send that over. We go to test. 1 second of yellow. 1, 2, 3, 4, and then the pedestrians get to walk. Everything works. No more lawsuits from pedestrians. We make a lot of money from those cool red light tickets. Our town is rich now. We get to hire a chief data officer. They come into our office. They're like, you're the one who always fiddles with those traffic light timings, right? Can't we use machine learning for that? Oh man, this demo is going to hell. The underscore. So then we run some machine learning. This looks like some sweet traffic light times. All right, we go out, we test it. Whoa. That's awfully fast. I think we have a case of bias in the machine learning here. I think the pedestrian speed data set, we might have recorded that on the day that the marathon was coming through town. All right, my example is getting really silly now. But hopefully it's hopefully it helps me make a point. This whole question of how to connect sort of software innovations like data science, machine learning, really just the fact that we are able to run stuff like code in the cloud, how to connect that to the operational technology that's running our factories. That's a source of a lot of discussion in industry right now. It's a source of a lot of opportunity for software engineers who want to do something in this new field. It's also been the source of a lot of products and, frankly, a lot of marketing bullshit over the years. The buzzwords to look for that capture all of this, one of them is Industrial Internet of Things, IIoT. In Europe, they call it Industry 4.0, but they effectively mean the same thing. Now, the way I would recommend thinking about this is that there are 2 control loops. The first control loop is the one that's running on the PLC. Milliseconds per iteration. It interfaces with the physical world. It does all the timing critical and safety critical things. It basically implements like the laws of nature or the laws of traffic. Two crossing streams of traffic can't have a green at the same time. That's the kind of stuff that happens in there. Then the second loop is the one that can influence the behavior of the first one, taking into account stuff like, what's the weather today? What's the traffic like somewhere else in town? Maybe some insight gleaned from machine learning applied to process data that we extracted from the first control loop previously. Those things might run every minute or every month. You might not know how long they take, definitely not real time. You might be querying databases, APIs. It might fail, and that's fine, because the first control loop is still running this process safely. You're just there to optimize and customize it. Many software engineers who learn about automation and control engineering for the first time, they think the objective is to replace this existing old stuff, the ladder logic. And I would recommend not taking that view. The way to go about this is to learn how to interface with what's already there, wrapping a layer of software around it, and generating value that way. Now, I've given you one tool so far for doing that, PyModBus, to emulate the Modbus protocol. I also spent just a little bit of time, maybe a little more than that, going through all of PyPI and looking for all the packages that implement any protocol that you can use to talk to an industrial automation equipment. And on the next 4 slides, which I'll go through very fast, I basically give you tables with those packages in increasing order of difficulty. Slide number 1. If you have a PLC from one of those vendors, there's actually a package on PyPI implementing the vendor's proprietary protocol. Use it. It might look like this. PyADS, an implementation of the ADS protocol from a vendor called Beckhoff, looks almost like the Modbus stuff we did, except you get variable names. That's cool. And you get to subscribe to variable changes instead of having to poll. So you get little conveniences like that by using the vendor protocols. Difficulty level number 2. We use Ethernet cables and IP addresses. Remember, that's what we were doing here earlier. There's an Ethernet cable, we use an IP address. So Modbus is the first one on this list. There are many, many other protocols that implement communication with PLCs this way. You just open a connection and you can do it. There's a whole bunch of libraries. If there isn't a library for your favorite protocol, import sockets, import C types, read the manual, just implement the right bytes, send them in the right order to the PLC. Bob's your uncle. I also want to call out OPC UA. I think of all the protocols I'm going over here, OPC UA is the one that everyone here will recognize as a clean API. It's relatively modern. It uses XML. It's discoverable, so you can connect to a PLC without knowing the variable names and addresses ahead of time. And the other reason I bring it up is that there is a project called FreeOPC UA, which has one Python package that implements the protocol, a second Python package that implements a client and server for the protocol, a third Python package that implements an async I/O client and server for the protocol, and the fourth one, which is on screen here, an awesome GUI app that you can actually use to connect to a PLC and explore what's on there and communicate with it, all written in Python. And they're great. It's an actively maintained project, very open to new contributors. So if you want to tinker in this field, this might be a good starting point. The remaining 2 difficulty levels, the list gets a little bit sparse. This is when we're doing networking without IP addresses. So we use an Ethernet cable, but to talk to somebody else, they don't have an IP address. That's a thing that actually is very uncommon in most software developers' lives these days, but very common in industrial automation, because TCP/IP is by design not real time. You don't know how long it's going to take. It's just a promise that it will eventually maybe kind of sort of happen. That obviously doesn't cut it when you have safety critical machinery. So a lot of other Ethernet-based protocols exist in industrial automation, and there are sometimes ways to interface with them and sometimes not, depending on how fast you need to be to do it. So EtherCAT is one that is a protocol that's implemented by this library here. I actually learned while researching this that Python, the standard library, has all the tools you need for this kind of networking, and these 2 packages that I mentioned down there, rawsocket.py and dnet, are actually great inspirations for how you do that kind of networking. It was very educational when I researched that. Finally, 4th level is all bets are off, custom cables, weird like serial things. If you find yourself in the land of serial cables and CAN bus, you'll have to start by buying some converter hardware and all these kind of things, and there might be some libraries available or not. I would recommend steering clear of that when you can. This could be my last slide, but as soon as I walk down those stairs, someone's going to come up and be like, what about MicroPython? What about my Raspberry Pi? That can do all the things that your PLC can do. There's like a 10-slide long answer to that. I'll give you the short one. First, your Raspberry Pi will likely not survive most of the environments that PLCs are deployed to. It's just from environmental conditions. Second, if you use Python on a Raspberry Pi to implement a safety-critical control system, you might also not survive it. So don't do that. And on that positive note, this is my last slide. If any of the things take a photo of this, I'm not going to leave it up very long. If any of the things in this talk were interesting to you, this is the collection of things I'm aware of where hobbyists can try these things out in a place where you can access them without being part of a big megacorp, and also that are somewhat affordable. That's all I have. Thank you very much.
Thanks, Jonas. I was